Good afternoon. This box just arrived from Mount Baker Mining and Metals, and it's full of Jason's gold ore. So I've got a few things I want to do with it, but first let's open it up and take a look. Let's see what we got. A bag. Inside the bag is a sandbag, and inside the sandbag is a bunch of rocks. And there's some finer material, some beautiful quartz. So the first thing I'm going to do is to pick through this and see if there's any specimens I want to take out of it and retain. So as I go, I'm separating out the waste rock, and some of this is really has heavy sulfides. In fact, when you break them open, you can smell the sulfur in some cases. So I'm going to bust these rocks up in my little crusher so that they'll fit into my rock grinder. You can see the massive sulfides in here. All right, well, here's the results of bashing up all those rocks. I removed the country rock, the waste rock. This is 1.5 kilograms. And I've got about 10 kilograms, a little bit under 10 kilograms of the good stuff. So I picked out all of the waste rock that I could find. There wasn't very much. And I busted it up to, 3/4 minus, so it'll fit into my grinding machine. So what I'm going to do is use this to grind some of this. I don't know if I'll do it all. It's a bit of work. I've got a 60 mesh screen, and so I'm going to classify it into here, and I'm going to return all of the stuff that's larger than 60 mesh back into the crushing machine. This is a flail mill. Super important is a respirator, and I like to use hearing protection for everything I do. I processed, a couple of kilograms maybe, and very fine, powdery, 60 mesh, and I need to change the carabiners on here. I've got another 2, and that's all I've got. So when those 2 are done, then I'm going to quit this part of it. So there's the situation inside. You can see the carabiners are failing, and this piece here is about to fail too. So this is it's basically kind of a toy, but it works, and I'm working on a much better one, but it's not finished yet. So there's the new carabiners on there. This will last another few kilograms. I probably get about 5 kilograms out of a set. So it's not really efficient, but it's great for field use. All right, about a half an hour of grinding, and I've got 3.8 kilograms of 60 minus. And here's the stuff that I couldn't get through the 60 mesh sieve. It's about 390 grams, so roughly 10%. What I do is I keep returning this through the machine over and over again, and eventually you'll get it all. Okay, so here's a rock that contains some gold. I'm going to put it, I'm going to use this magnifier, and we'll take a look at it up close. There's some gold in there associated with the sulfides. There's another speck in there, again associated with the sulfides. There's a kind of a free particle of gold. They're very tiny, the specks. There's another free particle of gold, I think, there. There's clearly gold associated with those sulfides, very tiny pieces of gold. Now I'm going to mix this as best I can, try to get a uniform sample. Because I want to try various methods of assaying this. Or extracting the gold, maybe a better way of saying it. And I want to compare those, so I'd like it to be as uniform as I can get it. Okay, now I want to divide this roughly into 4 and bag up some of it for later use. So if we use symmetry to our advantage or benefit, then this half should be the same as this half. And again, for the same reason or principle, that half and this half should be the same. All right, I got 3 parts here and 1 part there. So there should be roughly 3 kilograms in here and roughly 1 kilogram there, which is should suit my purposes very well. Okay, I got things nicely divided up, and I've got this pile left, and that's going to be the experiment of today. I'm going to divide that in half. All right, each cup's 113 grams. Okay, I'm going to start mixing up the charge. This is the crucible. It's an A5. Holds plenty of material. For our purposes, this is one of the ore samples. This is my flux mixture. Contains equal parts of Chapman's, borax, normal borax, you know, washing stuff, and normal soda ash, washing soda. So none of them are anhydrous. Now, I want to, I use 3-to-1 ratio of the flux to the ore. So that would be what, 340 grams roughly? And in the first batch, I'm going to use 30 grams of litharge. And it fills it up roughly halfway. And in that, I use a piece of iron steel. Okay, there's the 2 charges. Number 1 has the litharge, number 2 has the bismuth. Otherwise, they're completely identical. All right, the next experiment I'm going to take one of these bags. It has 215 grams of the ground up ore. And this water has a surfactant in it. And I'm going to pan it out. And remember, this is 60 mesh, ground to 60 mesh minus, which I don't think is fine enough to liberate all the gold. So I've panned it down this far, and I'm sure you can't see this on the video, but I see gold, tiny, tiny pieces of gold sitting on the surface as I'm panning it. So I have to be like ultra careful not to wash that microscopic gold, you know, right out the pan. Okay, pan down the best I can. You can see the line of gold there. And from experience, I know that these sulfides are quite heavy, so I don't know if there's gold locked up in there or not. But anyway, that's one of the purposes of this set of experiments, to see where the gold actually is and how to get it out. So now I'll snuffer up all this heavy stuff, put it in my little flat bottom beaker, and we can take a look at it with the high power loop. Okay, so here's the setup to take a look at this in more detail. I have this attaches to my cell phone. The cell phone goes on here, and then I can look at it through this mirror. So there's the gold, and that's got to be the finest gold I've ever seen. Those particles are maybe, I'm guessing, less than 50 microns. So that's 300 mesh or finer. Okay, the next step is I'm going to clean up this a bit with hydrochloric acid, just 30% hydrochloric acid in there. And I'm getting some bubbling. All right, I'm going to make Aqua Regia in the little beaker. There's some water, just tap water. About 4 milliliters of hydrochloric. And I'll add half a milliliter, which is 10 drops of nitric. 11 drops. And now we've got Aqua Regia. We'll let that finish reacting. All right, this has cooled down for an hour or so. Whoop! This falls totally out of the, let me get a hammer. So this is the lead. I'm expecting about 27 grams. And there's only 22. So I'll bust this up to see if I can find any more in here. I've looked through the slag. I don't see anything more, so that's a little bit unusual. I usually get much closer to the full amount of lead. Anyway, I lost 5 grams of lead there. And here's the bismuth pour. A good separation. Of course, there's no matte layer. A little bit of bismuth comes off on the slag. So, second strange thing is it's quite soft, which means it's alloyed with something, because pure bismuth is quite hard. 27.6, and I used 30. So lead and bismuth. And I've got my cupels in the oven, and they're heating up. Right, here's the chloroauric acid that we get from digesting gold in Aqua Regia. Notice the large amount of undissolved stuff in here, black. I imagine it's some kind of sulfide. Anyway, we'll continue. I added 11 drops of nitric, so 11 drops of saturated solution of urea will guarantee to kill the nitric. I've got a small amount of cotton in the bottom of that funnel. That'll do it. Filtered chloroauric acid from the gold ore. Remember, this was 215 grams worth of ore. Fresh batch of stannous chloride. 10 drops. So you can see the strong color change. We've got plenty of gold in that solution. It's pretty hard to see the transparency. So to get it a little bit lighter so that I can compare it to something else, I'm going to take half of it and put it into here. And then I'm going to take half again and put it into here. So each of these now contains 1/4 of the gold we originally had. And I'll dilute this one by a factor of 2. Now I've got a density that I can work with. So I'm going to put 10 drops of stannous chloride, just like I did originally. And now I've got a standard solution of gold as chloroauric acid. This is 2 milligrams of gold per milliliter of fluid. We'll start with 2 drops. And I'll add some water. And now I'm trying to compare the density of these two liquids. So I know from this is a little green, unfortunately, and that's contaminated with either copper or iron. That's okay. I'm kind of used to this test now. That is a little bit less dense in terms of the gold content than that. So I'm going to add a couple more drops. 1 drop. 1 drop and mix. And now to my eye, they're similar. So what we started with was 215 grams of gold ore, which we ground to 60 mesh, and I panned it down to the heavy stuff. I dissolved it in Aqua Regia, and then we found that it took roughly 12 drops of my standard solution to equal the density with using stannous chloride. So the weight of the gold in the solution that came from the gold ore is equal to, well, there's 12, it took 12 drops to equal it. And there's 1 milliliter is 20 drops. And it was 2 milligrams per milliliter, 1.2 milligrams of gold in our sample of 215 grams of ore. So the weight of the gold per metric ton is equal to 1.2 milligrams divided by 215 grams. And then there's 10 to the 6th grams per metric ton. And if we run that out, it's 5.6 grams per metric ton. This is bismuth, that's lead. There's a small bead in the lead, smaller, frankly, than I expected, and 0 in the bismuth. Well, there they are. This is the lead, this is the bismuth. And I figured out the bismuth mystery. There's little gold, tiny little gold balls scattered all over the bottom of this. So during the cupellation process, the bismuth must have spattered the gold. And that explains perhaps what I've seen in the past. I've seen this exact effect where I get a gold bead using lead and I don't get anything using bismuth, but now I understand what's happened. I don't know whether this was cupelled at 1770 degrees Fahrenheit. Maybe that's too hot for the bismuth and it spatters. I'll have to do some more experiments with that. But anyway, that appears to be where the gold went. So there's the little gold bead from the lead assay. Got a little bit of junk on it, but not too much. Those divisions are 250 microns. In other words, 1/4 of a millimeter. So it's about 400 microns in diameter. Okay, I'm going to use this apparatus to measure the weight of the bead. I've covered this balance before. It has a precision of about 20 micrograms and an accuracy which is maybe 50 micrograms. It's something like that. This is a standard set of calibrated weights that you can buy. It's not expensive. And here's the gold bead. It's in there somewhere. It's a tiny gold bead that we got from the fire assay. So we started with 113 grams of gold in the crucible. We just weighed the bead. We had 72 millivolts. This is just calibration here. But anyway, we weighed the bead, we calibrated the scale, and we ended up with a 1.3 milligram bead weight. The weight of the gold, or at least the weight of the precious metals, so there could be some silver, other stuff in there. The weight of the gold in metric tons then is 1.3 milligrams. We started with 113 grams, and then we multiply by 1 million grams per metric ton. 11.5 grams per metric ton. So I did a fire assay using lead, and I got 11 grams per metric ton roughly, and I estimate that's probably plus or minus 10%. I did an Aqua Regia digestion of panned out ore, and I got about half that. And I would say plus or minus 20 or 30% accuracy. So I think it's clear that I'm not getting as much, for whatever reason, in the chemical assay as I am in the fire assay. And that could be because the gold is still locked up in the sulfides. It may be that panning that microscopic material is too difficult to do, and some is escaping into the tailings. Those are open questions to answer. So, is density separation going to work? I think we have to work a lot more on that question, and I'll be making more videos covering that. How variable is the ore? Well, I found these ores are incredibly variable. I can take ore from a thin region in a gold vein, in a gold-bearing vein, and I can fire assay it and get results that vary plus or minus a factor of 2. So we don't know, but we do know that gold ore is extremely variable, and that's because we're talking about parts per million. So if you have one sizable chunk of gold in one rock, you can change the results by factors of 2 or more. Why does bismuth spatter the gold? So this is the second or perhaps the third time I've seen this problem with bismuth. I don't know what I'm doing wrong, but that's an open question that I want to answer. Also, if you recall, when I added the stannous chloride to the Aqua Regia that contained the chloroauric acid, the color turned a bit green. So there was some green and there was some, normal brown, purple color for gold. Well, green also indicates palladium. It could be that there was contamination with iron or copper, but the more I think about it, the more I think there might be palladium in that ore in addition to the gold.